Hello guys, welcome to day 20 of the Leetcode challenge. First of all, if you haven't subscribed to our channel, please do because we are posting daily updates and discussing a solution on this channel. Now let's look at today's question, right? So we are given the pre-order traversal of the binary search tree, and we need to construct the tree and return the root of the tree, right? Remember, the node consists of three values: a val, which stores the integer or the value in the node, and a left pointer and a right pointer. So first of all, what I'm thinking is, if we have this array, I'll actually tweak this example for better understanding to have 9, 5, 1, 7 instead of 8. Okay. Now we know that the first element is the root of the tree. This is a pre-order traversal, which means you put the node first, then the left pointer, then the right pointer. Okay. So we constructed the root, right, equals to 9. Now we keep a pointer here, right? This is our current node. And what we'll do is we'll always compare the next number to this current node. So if this is less than 9, then what we can do is we can safely append it to the left branch of this current node. Now we constructed 5 here. Now our current node pointer becomes this. Okay. And we see that there is a 1, and again this is less than the current node's value, so we constructed a node 1. Now there is a problem. Now we see 7. We need to either jump back to 5 or we need to append 7 to the right of the right branch of node 1, right? Why we cannot add 7 to the right branch of 1? Because we already have 5 as a limiting factor on any of the subtree formed by this one node, right? So this value, the rightmost value from the subtree rooted at 1 cannot be more than 5. So it has to be less than 5, right? So here what we need to do is we also need to maintain whether we can send this maximum value 5 to this node as well. So we need to keep log that what can the maximum value be. If it were to be 3 rather than 7, I would have appended 3 because it satisfies and it builds the tree 9, 5, 1, 3, right? It satisfies the constraint that it is less than 5. Now let's go back to our original values and see that it is 7. So we cannot append 7 to the right of 1. Now we need to go back to 5. So how do we do that? Either we maintain pointers to the parent, or what we can do is we can actually maintain a stack of nodes which define actually the path from root to this current node, path from root to current node, right? And once we do this, our top is actually the current node we are seeing, okay? And the bottom of the stack is root, right? So we'll always see that, okay, now here the current node is actually value 1. So if a 7 comes, and we also maintain that the maximum value we can have is 5, we compare the 7 to 5. We cannot insert this on top of 1 or the right of 1. So what we need to do is we just have to finish this node. There's nothing to be added in this subtree. This current node can be popped out, and what we reach a node whose value is 5, right? And for this 5, we should have maintained that this 5 subtree cannot have more than 9 value in any of the nodes, right? So we see that 7 satisfies the constraint that 7 is between 5 and the 9 maximum, right? So what we need to do is we need to insert 7 to the right of 5. Now let's consider if it were not 7, if it was say 12, okay, what would have changed? So if it were 12, we would have to pop this out because this does not satisfy the constraint that we can insert 12 into a subtree rooted by 5. So we pop out this, right? Now a stack just becomes the root of the tree, which is 9. And since it's the root, then we can have plus infinity, minus infinity in any of the subtree, right, as the minimum and the maximum value. So when we reach root as a current node, now we can safely insert 12 to the current node, which is valued at 9. right? So in this way, we have two conditions basically. If new number is less than current value, then we can safely go on inserting it, insert in left branch, else pop till we have satisfied this constraint, and once we do that, then insert in right branch. Okay, let us just code this algorithm and see if it works or not. Okay, great. Okay, let us code our solution in Python. So first of all, what we'll do is we'll define our root. We'll take the length of preorder array, return -1, return none actually. Okay, which means there is no root as such. Now we create a root which has 3 nodes, right? And the value of this root should be equal to preorder of 0 for the first node value. Right? What we can also do is once we construct this, right? Now we also need to define, we need to put this root in the stack, right? That is for sure, because this is our current node. And I also told you we need to maintain the minimum and the maximum value, right? So minimum and the maximum. And how do we define min and max? So let's define min equals to -infinity and max equals to +infinity. Okay, and I define infinity by something like 10 raised to 10. Okay, now this is our current path that we have seen, right? Current path, right? And once we define root, in the end we also need to return the root. Now here we will construct our BST. Okay. Done constructing BST. We need to see the rest of the numbers, right? For I in range 1 to n, num equals to preorder of 1, right? And this number, we need to construct a node, right? This is the new node. New node equals to 3 node of num. Okay. Now this is the new node, and we need to find where to insert this, right? So let us state the current. Let us see what is the current node's value, right? So current node, min and max. So this should be the top of the stack, right? Now this is our top of the stack. Now if num is less than current node dot value, right? What we need to do is we need to just insert this node to the left of the insert new node in left branch. So current node dot left equals to new node, right? And what else we need to do? We need to manipulate the current node pointer, right? And so that means inserting into the stack, right? So stack dot append. What we need to append? We need to append the current node, the min value, and the max value. So a max value actually will become, we need to insert the new node actually. Okay. Our max value will become current node okay, just fix in some variable naming current node dot value, because any subtree rooted by new node cannot have value more than what its parent had, right? Now this means insert in right branch, but which node, right branch of which node, right? So what we need to do is we need to check in the stack current node minimum maximum. We need to look at top of the stack and figure out if num satisfy the constraint that it can fit on the right branch of this current node or not. If it can fit, then go insert in right branch, right? Else we just need to abandon this node, which means we need to pop out this current node. Okay. Now if we fill the if condition, we assign it the new node to the right branch. Okay. Now we need to also insert a new node in the stack, which means it becomes the current node, right? Just like we did on line 32. Okay. Now the max remains same, but what is the min? The min should actually be the current node's value, right? Because we are coming from the right branch of our parent. So any of our subtree cannot have a less value than a parent's value. Now let's just run this code. Okay, n is not defined. Oh yeah, n equals to len of preorder. Okay, let me also do some more sanity checks if we are missing anything. Okay, here it should be val when comparing. Right, so if we insert here, then we just need to create this. We can actually put our step dot append here. Okay, right. Let's run this code and submit our code. Okay, great. So doing 3 questions with a stack is a bit tricky, but you just need to maintain some information in the stack, doing an iterative version rather than a recursive version. Right. So we have done actually like an order n solution here using a stack. Let me know in comments how you like the solution and if any particular problem you need to be discussed on our channel for Leetcode. Subscribe to our channel, share our videos, like our videos. Thank you so much for watching again. Bye.